Good evening everyone, good evening. I welcome you all again to NEET Elite. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Yes, just let me know in the chat box if I'm audible and visible to every single guy. Let me know in the chat box with some thumbs ups. Hello Namami, hello Ashwarya, hi Varsni, hello Raj, hi Sujit. Hello Kirtan, hello Anish, hi Kopo, hi Sahifa, hello Tushar, hello Oshika, hello Maharaj, walaikum salam, hello Shiva, hi Monisha, hello Farooq. Welcome back everyone, welcome back. Just let me know in the chat box fast if I'm audible and visible to everyone. Give me some green signal from the chat box, yes. Give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you guys or not. Yes? That's great, Tushar. That's wonderful. Perfect, guys. Perfect. I'm doing good. So people, as you all must be knowing, tonight it's going to be, I guess, the 6th session, yeah? Right? Yes. Tonight it's going to be the 6th session from the chapter Atomic Structure, right? In the last session, if you remember, we started something called as Bohr's theory, right? And in the last session itself, we derived some formulas related to the Bohr's theory, which was all about the radius of the nth orbit, velocity of the nth orbit, time period, frequency, right? Everything was discussed in detail. Now, the point is what we are going to discuss in the tonight's session. Well, people, in the tonight's session, we are going to talk about the total energy possessed by the electron in the nth orbit, right? We are going to talk about the kinetic energy possessed by the electron. Similarly, we are going to talk about the potential energy possessed by the electron in the nth orbit as well. Okay, so these are some of the important topics, very important topics which we are going to cover in the tonight's session, right? And the next session of this atomic structure is going to be hydrogen spectrum, right? Perfect. So people, before starting the session, the ones who are new to the channel, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher writer on this NEET Elite channel, yeah? The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which will be taking live on this NEET Elite channel. Yes? Perfect. NEET motivation, you just refresh your page once because I can see on my side connectivity is all okay, right? Kirtan, I cannot teach physics, bro. Okay. So people, let me know in the chat box if you guys are super duper excited about the session so that we can start the session directly without wasting a lot of your time. Yes? Let me know in the chat box if you guys are super duper excited about the session, right? Let me know in the chat box with some thumbs ups, I'm all good, Rizwan. Thank you. Perfect, guys. Perfect. So let's get started with the tonight's session then. Okay. Alright, so people, the first thing which we are going to cover in the tonight's session, that's going to be energy of electron in the Bohr's orbit, right? How do we calculate the energy possessed by the electron in any Bohr's orbit? Yes, how do we do that? Okay, understand and note down every single thing which I'll be mentioning on the screen, okay? For example, I'm taking a single electron species, okay? Single electron species. I told you in the last session, right? That species which just contains one electron in it, okay? So basically, I'm going to take either hydrogen or hydrogen-like species, okay? For example, I'm taking a single electron species over here whose atomic number is Z, right? I'm taking a single electron species over here whose atomic number is Z, right? Let's assume this is the nucleus of this single electron species, okay? And this is the shell in which your electron is there, okay? Now people understand few important things. Note down every single thing. I'm saying the single electron species which I have definitely it will be having one electron over here. Okay, let's assume this electron is in shell number 1, for example, okay. Now first thing guys, since the atomic number of this single electron species is Z, so this species over here is going to contain Z number of protons. So first of all, I'll say number of protons in this single electron species is simply going to be equal to the value of atomic number Z, right? And we know on one proton, what is the charge present on one proton? The charge present on one proton, as you all must be knowing, that is E. So I'll say the charge present on Z protons is going to be simply Z multiplied by E, okay, with a plus sign, right? Yes. And all the protons, they lie inside the nucleus, we know it. So if I ask you what is the net charge present in the nucleus, you will clearly say Z multiplied by E with the sign positive over here. This is the net charge present inside the nucleus, correct? Right? Now people, this is the electron which is revolving around the nucleus, right? An electron will be definitely carrying the charge whose magnitude is same as that of the charge present on proton. It is going to be E, right? And the sign of this charge is definitely going to be negative, right? Let's say this electron is revolving around the nucleus, and at this instant, right, the electron is moving with the velocity v, for example, okay? So first thing, if the electron is moving with the velocity v, can I say this electron will have some kinetic energy right here? Absolutely, it's going to have some kinetic energy. So I'll first of all say the kinetic energy possessed by the electron is equal to half of mv square, right? This is the kinetic energy possessed by the electron which is moving around the nucleus, okay? Now at the same time, since this electron carries a negative charge, nucleus carries the positive charge, let's say this distance between them is r, right? So can I say over here there will be some electrostatic force of attraction between the nucleus and this electron? Absolutely. Due to which this electron will possess some potential energy as well, right? So I can say something as potential energy possessed by the electron will be equal. In the last session, if you remember, I have told you I have given you the simple formula by means of which you can calculate the potential energy. That's equal to K Q1 Q2 divided by R, right? Let's assume Q1 is the charge present inside the nucleus and Q2 is the charge present on the electron, okay? So people, can I say potential energy possessed by the electron over here? That's going to be K. Instead of Q1, I'm going to write Z multiplied by E, okay? And instead of Q2, which is the charge present on electron, that's simply going to be minus E divided by what? Divided by R, okay? So this value over here will simply come out to be minus K Z E square divided by R. This is the potential energy possessed by the electron right here, because this electron right here is under the influence of the nucleus, okay? Point number 1, right? Now people, this electron right here, it has got the kinetic energy, it has got the potential energy. If I ask you what is the total energy possessed by this electron over here, total energy possessed by the electron, which I'm representing by En, total energy possessed by the electron is simply going to be equal to the sum of kinetic energy possessed by the electron and the potential energy possessed by the electron, right? This is the total energy which the electron has, the sum of kinetic and potential energy, yes? Now people, understand few important things which I'm going to tell you now. First of all, I told you kinetic energy possessed by the electron is half of mv square, right? I'm writing it over here again. Kinetic energy possessed by the electron is half of mv square. If you remember the last session, I told you as per the Bohr theory is concerned. In the last session, I gave you one simple equation that was mvr, right? Or let me not write this, let me write the other equation that was mv square divided by r is equal to k ze square divided by r square. I hope you remember this equation, okay? Right? The necessary centripetal force for the electron to move in the circular path is being provided by the electrostatic force of attraction between the nucleus and the electron. I hope you remember this, okay? Now people understand. Can I say this r and this r gets cancelled out? So from here you get the value of mv square as k ze square divided by r, right? Okay. Now in this equation we have got something as kinetic energy is equal to half of mv square. Instead of mv square I can write something as k ze square divided by r, right? This is the kinetic energy possessed by the electron right now which is going to be k ze square divided by 2r. Correct? This is the kinetic energy possessed by the electron, right? This is the kinetic energy. And what is the potential energy possessed by the electron? Potential energy possessed by the electron is minus k ze square divided by r, right? You got to know the kinetic energy as well as the potential energy possessed by the electron, so you can calculate the total energy which this electron has right now. Okay? You can calculate the total energy possessed by the electron. And how do I calculate that? As simple as that. I have told you a few minutes back, the total energy possessed by the electron is the sum of kinetic energy and potential energy possessed by it. Okay? So people, I can say the total energy which I'm representing by En is equal to, what is the value of kinetic energy? It's going to be k ze square divided by 2r, right? Plus potential energy possessed by the electron, that's equal to minus times k ze square divided by r. Okay, this is something which I got till now. So people, I can say simply like this, total energy possessed by the electron is going to be equal to minus times k ze square divided by what? Divided by 2r over here. This is the total energy possessed by the electron, right? Now, if you compare these equations, let me call this equation, let me recall this equation, and let me recall this equation. What all things can you predict from these equations? Can you let me know in the chat box what all things you are going to predict from these equations? A very, very simple equations you got. Well, people, I can understand one thing from here. See, this is the total energy possessed by the electron. This is the kinetic energy possessed by the electron. So can I say kinetic energy is basically minus times the total energy, right? Kinetic energy possessed by the electron is basically minus times the total energy possessed by the electron. Well, if you look at these formulas, they are one and the same, right? It is just the sign is different. It is just the sign is different. So I can say something like this. Kinetic energy of the electron right now is going to be minus times the total energy possessed by the electron. Point number one. Point number one, right? Okay, point number one. Now we will understand few more important things. See, or you can write something as the total energy possessed by the electron is equal to minus times the kinetic energy possessed by the electron, which is also equal to one more thing. Now, if I want you guys to compare this equation and this equation, right? If I want you guys to compare this equation and this equation, right? I can say total energy possessed by the electron. Total energy possessed by the electron is equal to 1 by 2 I'm keeping outside. 1 by 2 I'm keeping outside. Minus k ze square by r. Minus k ze square divided by r. That's something which I call as potential energy. Absolutely, right? So I got to know something as just a second. I got to know potential energy is basically equal to 2 times the total energy possessed by the electron, right? Okay, this is one more equation which I got. These are some important results which I want you all to take a note of, right? Okay, absolutely guys. See, you can write these two equations in a single equation form. You can say kinetic energy of the electron is equal to minus times total energy, or you can say total energy of the electron is equal to minus times kinetic energy, which is also going to be equal to potential energy of the electron divided by 2. This is the major equation which you guys are going to remember over here. You can let me know in the chat box if every single thing is clear till here, right? You can let me know in the chat box fast. Let me know in the chat box if everything is clear till here, right? This is the total energy possessed by the electron, which is equal to minus times its kinetic energy, right? Which is equal to potential energy of the electron divided by 2. Okay, perfect. Let me know fast. Is it clear? Right? Is it clear to everyone? Yes? Perfecto. Wonderful. Now people, understand one more important thing. I'm sure you have noted down every single thing till here. Let me tell you some important things as well. We got to know the total energy possessed by the electron is equal to minus times, this is k, this is z e square divided by 2r, right? This is the equation which I got, right? This is how we calculate the total energy possessed by the electron in any Bohr's orbit of hydrogen-like species. Okay. Now, first thing, in the last session, if you remember, I gave you one formula to calculate radius. I hope you remember that as well. What was that? What was that formula all about? If you remember, radius of electron in the nth orbit is equal to n square h square, or was it nh? People, can you let me know what was the formula all about? It was, just give me a second, it was n square h square divided by 4 pi square m this was k z e square, right? This was the formula by means of which we could calculate the radius of the nth Bohr's orbit, if you remember. I hope you remember this, right? Radius of the electron in nth Bohr's orbit is equal to n square h square divided by 4 pi square m k z e square. This is the formula which we derived in the last session, right? Okay. Now people, if I put this value of R into this equation, what do I get? I'll get something as total energy possessed by the electron in the nth orbit is equal to minus k z e square divided by 2. Instead of R, what I'll be writing? I'll be writing n square h square, and all these terms, they'll go up. It's going to be 4 pi square. This is m, this is k, this is z e square over here, right? Yes, I'm sure it's clear to everyone. Now people, over here we have got z, right here we have got z, so it's going to be z square. So I'm going to generalize it like this. En, energy, total energy possessed by the electron in the nth orbit of the hydrogen-like species is going to be minus k, then I'm writing e square, then I'm writing e square, then I'm writing 4, then I'm writing pi square, then I'm writing m, then I'm writing k, right? This is e square, this is e square, it becomes e raised power 4, right? Z square I'm writing separately, okay, divided by 2 I'm writing over here, right? This is h square, and n square I'm writing separately, okay? Now people, in this equation, if you can see one thing, there are only two variables in this equation. One is this z, one is this n. All the other things right here are constants. All the other things right here are constants, right? If you put the values of these constants into this equation, I'll be getting something as the total energy possessed by the electron will be minus 13.6 z square divided by n square electron volts. This is the formula which I want you guys to remember from now onwards. This is the total energy possessed by the electron in the nth Bohr's orbit, right? Okay, let me know in the chat box if everything is clear till here, right? Let me know fast. This is the total energy possessed by the electron when the electron is present in any nth Bohr's orbit. Minus 13.6 z square divided by n square, right? Well people, if you got the total energy possessed by the electron, you can calculate kinetic energy, you can calculate the potential energy, right? Okay. Absolutely. So we got to know the total energy possessed by the electron is minus 13.6 z square by n square. But already I had mentioned the total energy possessed by the electron is minus times its kinetic energy. Or you can say kinetic energy is minus times the total energy. So from here, you can say kinetic energy possessed by the electron is 13.6 z square divided by n square electron volts, correct? This is the kinetic energy which is possessed by the electron in the nth Bohr's orbit, right? Okay. I'm sure it's clear to everyone. Now people, at the same time, you can calculate the potential energy possessed by the electron in the nth Bohr's orbit as well. What that's going to be all about? That's going to be minus 27.2 z square divided by n square electron volts, right? These are the three important results which I want you guys to take a note of. And out of three important results, I'll be frequently using this result, which is the total energy possessed by the electron in the nth Bohr's orbit, right? Now people, you would have noticed one important thing, that there's a negative sign over here. The total energy possessed by the electron is minus times 13.6 z square by n square. This negative sign, it simply tells us that the electron is under the influence of the nucleus. There is attraction between nucleus and the electron over here, right? So this negative sign, it has got the significance. What is the significance of this negative sign? This negative sign clearly tells me that the electron is under the influence of the nucleus. The electron and the nucleus, they are having some sort of attraction in between them, right? So this negative sign, it simply shows the attraction between the nucleus and the electron, which is present in the nth Bohr's orbit, right? You can let me know if it is clear till here, right? Let me know first if it is clear till here so that I can move on to everyone. Let me know fast, let me know fast. All right, Aleem, I'll be doing that. I didn't check my Instagram, I'll check it out. I'll check it out. So I'm sure everything is clear till here, right? I'm sure about it. Perfect, guys. Now let's move on and talk about something really interesting. What is that going to be? See, what we got to know till now, we got to know the total energy possessed by the electron in the nth Bohr's orbit is minus 13.6 z square divided by n square, right? Okay. Now people understand. Can I say the total energy possessed by the electron is inversely proportional to n over here, right? We can say that. Can we say that? Can we say that? Understand, if I increase the value of n, if I increase the value of n, right? On increasing the value of n, what is going to happen? What is going to happen? Z square divided by n square will decrease, right? If I increase the value of n, z square divided by n square, it will start to decrease. Okay, so I can say 13.6 z square divided by n square, it will also decrease. It will also decrease, right? If I multiply this by minus, so minus times 13.6 z square divided by n square, this term will definitely increase. And what do we call this term as? This term is something which we call as total energy possessed by the electron in the nth Bohr's orbit, right? So can I say something like this? As the shell number increases, as the Bohr's orbit increases, as the electron goes far from the nucleus, what happens to the total energy of the electron? Total energy of the electron increases. Yes, perfect. As the shell number increases, let me write it in the form of a statement. As the shell number increases, as the shell number increases, the total energy possessed by the electron, that increases, right? Okay. Is it clear to everyone till here? Let me know fast in the chat box. Let me know fast in the chat box, right? Let me know fast. Perfect, guys. Wonderful. Exactly. As the shell number increases, the total energy possessed by the electron, that also increases, right? This is one important conclusion which you need to take a note of, correct? Okay. Now, people, let's move on and let's talk about a few more stuff. These are something which I've discussed, which I've derived till now, right? These are few things, and these are the energy formulas which we have derived too, right? And this is the statement which I've already mentioned on the screen. As the value of n increases, the total energy of the electron increases. Okay, perfect. Now let's talk about the hydrogen atom in particular, right? Let's talk about the hydrogen atom in particular. Let's see what happens in case of hydrogen atom to the energies of different Bohr's orbits. Okay, understand properly what I'm going to say. Yeah. First of all, let me write the formula to calculate the total energy possessed by the electron. The total energy possessed by the electron is given by the formula En is equal to minus 13.6 Z square divided by N square electron volts, right? This is the formula which we have. Point number one. Now, people, in case of hydrogen atom, what is the value of Z? Value of Z is 1. Atomic number of hydrogen is 1, right? Now, people, I'm going to draw different energy states of hydrogen. Understand properly what I'm going to do. First of all, I'm talking about hydrogen. Let's assume this is the energy state 1 for hydrogen. This is the first energy state of hydrogen atom, right? Let's assume this is the first energy state of hydrogen atom. Let's assume this is the second energy state of hydrogen atom, N is equal to 2. Let's assume this is the third energy state of hydrogen atom, right? Let's assume this is the fourth energy state of hydrogen atom, and let's assume over here, somewhere here, N is equal to infinity, right? Let's assume all these things. First of all, this N is equal to 1. This is something which we call as ground state of hydrogen atom, right? Ground state of hydrogen atom. N is equal to 2. This is something which we call as first excited state of hydrogen atom. This is called as first excited state. N is equal to 3 is something which I call as second excited state. N is equal to 4 is called as third excited state, right? Yes. Okay, and in between somewhere over here, the nth energy state, I'll be calling this as, the nth shell, the nth orbit, I'll be calling it as n minus 1th energy state. Okay, in between somewhere here, right? Now, people, few important things which you need to take a note of. First of all, I'm talking about hydrogen atom, and in case of hydrogen atom, the value of Z is 1. We know it, right? If the electron is present in the first shell, first energy state of hydrogen, how much energy this electron possesses? I'll be using this formula. En is equal to minus 13.6 Z square by N square. Since the electron is in the first shell, so N value is 1. Since we are talking about hydrogen atom, the value of Z is also 1. So the energy which the electron carries over here, which I'm representing by E1, it's going to be minus 13.6 electron volts, right? This is the energy which this electron carries when it is present in the first shell, right? Okay. Similarly, when the same electron goes to shell number 2, how much energy the same electron carries when it moves to shell number 2? I'll be writing it as E2. So E2 will be equal to, put the value of N as 2 over here. So it becomes minus 13.6 divided by 4. So it becomes something as minus 3.4 electron volts, correct? This is the energy possessed by the electron when it is in the second shell of the hydrogen atom, correct? Now similarly, when the electron moves into the third shell, when the electron moves into the second energy state of the hydrogen atom, how much energy it carries? I'm representing that by E3. E3 value will be equal simply, since Z value is automatically 1 because we are talking about hydrogen, N value is 3, 3 ka square is 9, right? 13.6 divided by 9, it is going to be how much? Minus 1.8 something, yes? Okay, right? Can you clear it? Can you clear it? Or people, I have already made this diagram over here. You can check it out. You can check it out exactly. You got to know how to calculate the energy of the electron in different energy states of hydrogen, right? Now understand. When the electron is in the first energy state, this is the energy carried by the electron. In the second energy state, in the second shell, this much amount of energy the electron carries. This much amount of energy the electron carries. This much amount of energy the electron carries when it is in fourth shell. And when the electron reaches to infinity, when the electron is present at infinity, okay, what does that mean? See, E is equal to minus 13.6 Z square divided by N square electron volts. When this N approaches towards infinity, division by infinity is 0, right? So I would say when the electron moves to infinity, the energy possessed by the electron will be simply taken as 0, correct? Yes, I'm sure it's clear to everyone, right? Now people understand. Now people understand. If I'll ask you, what is the energy gap between first and the second shell? Energy gap between first and the second shell. The first shell carries the energy of minus 13.6 electron volts. Second shell carries the energy of minus 3.4 electron volts. What is the difference between these two energy shells over here? The difference between these two energy shells, which I'm representing by delta E, is equal to 10.2 electron volts, right? Similarly, between second and third shell, what is the difference? What is the energy gap? Energy gap, which I'm representing by delta E, the energy gap between second and the third shell is 1.89. Since you know the values, you just need to subtract them, right? Or let me show you how I got this 1.89 over here. See, I'm basically calculating the energy gap between shell number 2 and shell number 3, right? See, I'm basically calculating the energy gap between shell number 2 and shell number 3. So I'm writing it like this. Delta E is equal to E3 minus E2, okay? What is the value of energy possessed by the electron when it is in shell number 3? When it's in shell number 3, the energy possessed by it is 1.5 minus, what is the value of E2? E2 is minus 3.4, right? Well, people, if you just do the calculation, you'll be getting the value exactly to be 1.89 electron volts, right? So this 1.89 electron volts, this is basically the energy gap between the second and the third shell. Similarly, the energy gap between first and the fourth shell, that is going to be E4 minus E1. E4 minus E1, E4 minus E1, this value will come out to be 12.75 electron volts, right? Well, we will understand, you would have noticed one important thing over here. The energy gap between first and second shell is 10.2 electron volts. Similarly, energy gap between second shell and third shell is 1.89 electron volts. So what is happening to the energy gaps? What is happening to the successive energy gaps? Are these energy gaps increasing or decreasing, right? What is happening to the successive energy gaps? Can I say the successive energy gaps keeps on decreasing as the N goes on, right? As the N keeps on increasing, right? Okay. So first important thing which you need to take a note of, I'm writing it over here. The energy gaps, the successive energy gaps I'll write, okay? The successive energy gap keeps on decreasing as the value of N increases, right? Is it clear to everyone? Let me know fast. Let me know fast in the chat box. Now people, there are some important things which you need to know over here, which you need to understand right here. As I told you in the last session, when the electron moves from lower energy state to higher energy state, it absorbs energy, right? When the electron moves from higher energy state to lower energy state, it emits energy, right? Now people, if the electron in the hydrogen atom has to go from shell number 1 to shell number 2, this much amount of energy will be absorbed by the electron, then the electron makes a transition from shell number 1 to shell number 2. Similarly, if the electron wants to make a transition from shell number 2 to shell number 3, how much energy I need to supply? I need to supply this much amount of energy to this electron, then only it will make a transition from shell number 2 to shell number 3. Yes? If I want the electron to go directly from shell number 1 to shell number 3, if I want the electron to go directly from shell number 1 to shell number 3, how much energy do I need to supply? How much energy is absorbed by this electron? If you want this electron to go directly from shell number 1 to shell number 3, since this much energy is the gap, I mean this is the energy gap between third and the first one, so this much amount of energy you need to provide, you need to supply, this much amount of energy electron has to absorb, then only it can move from shell number 1 to shell number 3. Similarly, if I want the electron to go directly from shell number 1 to shell number 4, I need to supply energy, because whenever electron makes a transition from lower energy state to higher energy state, it absorbs energy. Now, right here, the electron has to go from shell number 1 to shell number 4. So how much energy do I need to supply? I need to supply this much amount of energy to the electron. Then directly, it's going to go from shell number 1 to shell number 4, right? Can you let me know fast if it is clear to everyone? Can you let me know fast in the chat box with some thumbs ups? Yeah? Let me know fast in the chat box if every single thing is clear to every single guy. Okay? Absolutely, Raja. For NEET 2021, you can watch it. Absolutely. Let me know fast. Let me know fast if it is clear. Yeah? Perfect. Wonderful. I'm sure everything is clear till here. Now, people, if I'll ask you one thing. In the last session, I told you when the electron makes a transition from higher energy state to lower energy state, it emits energy. It emits energy, right? So, for example, if the electron is right now in shell number 3 and it has to go directly to shell number 1, okay, from shell number 3 to shell number 1, the electron is moving from higher energy state to lower energy state. Definitely, electron will be emitting energy. How much energy it will be emitting? Whatever is the energy gap between these two shells, this much amount of energy the electron will be emitting when it will be making a transition from shell number 3 to shell number 1, right? Similarly, when the electron makes a transition from shell number 4 to shell number 1, it will be emitting energy. How much energy it will be emitting? It will be emitting this much amount of energy in the form of photons, right? Yes, as simple as that. Similarly, if the electron has to make a transition from 2 to 1, this much amount of energy electron will be emitting, right? So I want you guys to remember these values, because these are really, really very important. Because if you remember these values, then your calculation part will become faster. Okay? You can solve the equations in lesser time, right? Okay? Perfect. Perfect, perfect. Let me know in the chat box if everything is clear so that I can move on. Yeah, you can take a screenshot of it in 3, 2, 1, and now. Now, this was all about the hydrogen atom. Now, let's talk about something called as hydrogen-like atoms, right? I mean, hydrogen-like species. How do we calculate energy in case of hydrogen-like species? This is something which I've told you. As the number of shells increases, the energy gap between successful levels, it decreases. Yes? Now, people, let's talk about the same thing for what? For hydrogen-like species, right? Hydrogen-like species means those species which just contain one electron, right? See, guys, these are the energy states of the hydrogen-like species, right? Now, see how I got these. First of all, right now I'm talking about hydrogen-like species, first of all. Let's say I'm talking about hydrogen-like species whose atomic number is Z, right? The total energy possessed by the electron in the nth Bohr's orbit, it's given by the formula minus 13.6 Z square divided by N square electron volts. Absolutely. Okay. If I'm talking about the hydrogen-like species whose atomic number is Z, if the electron is present in the first shell, right? How much energy the electron possesses? Put the value of N as 1 over here. So you get the energy of electron as minus 13.6 Z square. This is the energy which the electron possesses when it is present in the first shell of hydrogen-like species. Similarly, put the value of N as 2 if the electron is in second shell. Put the value of N as 2 over here, right? Okay, so you get minus 13.6 divided by 4 Z square, which is going to be minus 3.5 4z square. This is the energy possessed by the electron when it is in the second shell. Similarly, this much is the energy possessed by the electron when it is in the third shell, energy possessed by the electron when it is in the fourth shell. Similarly, when the electron will be present at infinity, how much energy electron possess? Energy possessed by the electron when it's at the infinite shell, it is going to be 0. Yes? Okay. Right? I'm sure it's clear to everyone. Similarly, the same way you can calculate the energy gaps. What is the energy gap between first and the second shell over here? This much is the energy gap. You can calculate it. If you want to calculate the energy gap between first and 2, you will simply say delta E, which is going to be E2 minus E1, right? E2 value, you already know that is minus 3.4. That is minus 3.4 Z square. Minus E1 value, you already know that is minus 13.6 Z square. So the value over here will come out to be 10.2 Z square electron volts. This is basically the energy gap between first and the second shell. Similarly, you can calculate the energy gap between first and third shell, energy gap between second and third shell, and so on. The similar things you are going to do in case of hydrogen-like species as well. It is just whatever were the numbers given in the earlier case. After those numbers, you are going to write Z square. Rest the numbers are same. In the earlier case, it was minus 13.6, it was minus 3.4, it was minus 1.51, it was minus 0.85. Now, just put Z square with these values everywhere. You are going to get the same results for the hydrogen-like species as well. I'm sure it's clear till here, right? Okay, clear till here? Let me know fast in the chat box. Is every single thing clear? Perfect, guys. Let's move on and talk about few graphs related to the total energy. Let's try to make certain graphs related to the total energy, right? First of all, what is the formula to calculate total energy possessed by the electron in the nth orbit? It is En is equal to minus 13.6 Z square divided by n square electron volts, right? Now, first thing, I'm keeping Z as constant. If Z is constant, I'm keeping Z constant. I'm keeping Z constant. Now, the first curve, keeping Z constant, the first curve which I'm plotting, that is going to be between energy of electron, En, total energy possessed by the electron, versus, for example, n square, right? Versus n square, right? The first curve which I'm making right here, that's going to be En, total energy possessed by the electron, versus n square, keeping Z constant, right? Similarly, the second curve which I'm drawing over here, which I'm plotting over here, is between total energy possessed by the electron versus 1 by n square, versus 1 by n square. What is going to be the nature of the curve over here? Understand. I'm plotting total energy along y-axis, I'm plotting n square along x-axis. Total energy I'm plotting along y-axis, right? And n square I'm plotting along x-axis. Y and x, are these directly proportional or inversely proportional? These are inversely proportional to each other. And whenever I need to plot a curve between two variables which are inversely proportional to each other, what is the nature of the curve? Nature of the curve is rectangular hyperbola. So is it going to be the rectangular hyperbola like this? No way. Why is that? Why is that? Because you have got the minus sign over here. So you are simply going to take the reflection, or simply you are going to make this hyperbola in this quadrant over here and erase this one because you have got minus sign in the front. So this is basically the curve between the total energy possessed by the electron and n square, keeping what constant? Keeping Z constant, right? Okay. Whatever curve we were making in the first quadrant, same curves you are going to make in the fourth quadrant now. Yes? Okay. Now similarly, guys, if you want to plot a curve between En versus 1 by n, En versus 1 by n, okay? Now people, 1 by n square I'm plotting along y-axis, right? So first thing, total energy formula, En is equal to minus 13.6 Z square, I'll be writing it as 1 by n square, correct? So I'm plotting this En along y-axis, I'm plotting this 1 by n square along x-axis, right? So instead of En, I'm going to write y. Instead of 1 by n square, I'm going to write x. So this becomes the slope. Y is equal to minus mx. Y is equal to minus mx, right? Y is equal to minus mx. It's going to be a straight line, but with a negative slope right here. Yes? Okay. Right? And what is the slope of this curve? Slope of this curve is right here equal to minus 13.6 Z square. This is the slope of the curve, right? I'm sure it's clear to everyone. Okay, simple two basic curves regarding the energy and the n square energy versus 1 by n square, right? Now people, one more important thing. In these two curves which I have drawn, I had kept Z as constant. Now the other two curves I'm going to plot, Okay, and for those two curves, I'm keeping n as constant. Now I'm going to keep n as constant. Okay, I've kept n as constant. That means n square becomes constant. Okay, now I'm going to plot a curve. The curve is between the total energy. The curve is between the total energy possessed by the electron versus what? Versus z square. This is the first curve which I'm plotting, right? Between total energy possessed by the electron and z square. And the second curve which I'm plotting right here is between the total energy possessed by the electron versus z. These are the two curves which I'm going to plot over here. Yes, understand. En versus z square. So let me write the formula again. En is equal to minus 13.6 divided by n square multiplied by what? Multiplied by z square. So people, along y-axis I'm plotting total energy. Along x-axis I'm plotting z square. So instead of this En, I'm going to simply write y. Yes. Instead of z square, I'm going to write x. Okay. So this all becomes minus m. So y is equal to minus mx. As you all must be knowing, y is equal to minus mx is a straight line, but the slope is negative. And slope of this curve over here is equal to minus 13.6 divided by n square. This is the slope of the curve. Yes. Okay. Similarly, guys, En versus Z. Let me write the formula again. En is equal to, just a second, guys. En versus Z. Okay. En is equal to minus 13.6 divided by n square, and this is Z square, right? So first thing, I'm plotting total energy along y-axis. I'm plotting Z along x-axis. So instead of this En, I'm going to write y. Okay. Instead of this Z, I'm going to write x. But this is z ka square, so it becomes x ka square, right? And this whole is a constant, right? And sign is minus. Y is equal to minus kx square. What is the nature of the curve? If it was y is equal to kx square, the nature of the curve was parabola opening upwards. But it is y is equal to minus km square. It is going to be the parabola, but opening downwards, right? So the curve is going to be like this, right? I'm sure it's clear to everyone. You can let me know in the chat box if it is clear to everyone. Let me know fast if every single thing is clear till here. Yeah? Let me know fast. If every single thing is clear till here. Yeah? Tushar, just drag the video a little back, it'll be a replay for you. Okay? Yes, Animesh, you need to wait for it, bro. Yes? Alright, now people, these were the total energy curves, right? Now let's try to draw some kinetic energy curves. And kinetic energy curves are simple. Where are the kinetic energy curves? Well, this is the kinetic energy formula, okay? Kinetic energy curves are going to be simple. If z is constant, kinetic energy versus n square is going to be hyperbola like this, right? And this is kinetic energy versus 1 by n square, right? Because you do not have minus sign over here. I'm sure you can draw these curves now. These are two more curves regarding kinetic energy versus Z over here. I'm sure everything is clear. Yeah? Okay. Now comes something called as ionization energy. How do we define the term ionization energy, right? That's the point now. I'm sure everything is clear. People, I did not start the hydrogen spectrum yet. That's something which I'll be letting you know in the next session. That is again going to be one of the most important sessions from this chapter, okay? Now let's talk about something called as ionization energy. How do we define the ionization energy? Okay, basically ionization energy, its actual definition we are going to study in the periodic classification, which is going to be our next chapter. But over here, I'll be just giving you a little bit overview of this ionization energy. What is ionization energy all about? What is ionization energy all about? Look at its definition. The energy required to remove the electron from the valence shell of the atom is called as ionization energy. What does that mean? See, what does that mean? For example, I'm talking about the hydrogen-like species. That means I'm talking about the single electron species whose atomic number is Z. Right? Okay. Let's say this is the nucleus, right? This is the nucleus. Shell number 1, shell number 2, shell number 3, shell number 4, and so on, right? If it is the hydrogen-like species, that means there will be only one electron in it, right? Because it's a single electron species, and that single electron species is going to be present in shell number 1, right? That single electron is going to be present in the shell number 1, okay? Now people, in this hydrogen-like species, in this hydrogen-like species, the amount of energy which is needed, to remove this electron, from the atom is what I call as ionization energy. So what does that mean? Basically, what I need to do over here is I need to make a transition of this electron from shell number 1 to shell number infinity. That means the electron is going out of the atom. The electron is going out from the influence of the atom, right? Okay, when the electron reaches to n is equal to infinity, that actually means electron won't be under the influence of the nucleus over here at infinity, right? So the amount of energy which is needed to knock out the electron from the valence shell of the hydrogen-like species, that's something which I call as ionization energy. That simply means you need to make a transition for this electron from n is equal to 1 to n is equal to infinity. When the electron makes a transition from n is equal to 1 to n is equal to infinity, that actually means the electron is out of the influence of the nucleus. That actually means the electron is out of the influence of the nucleus, right? Yes? I'm sure it's clear to everyone. So whenever you talk about the ionization energy, that simply means you are going to make the transition of the electron from shell number 1 to shell number infinity, right? Okay. So if the electron is going to make a transition from shell number 1 to shell number infinity, right? So that means electron is moving from low energy state to higher energy state. So this electron has to this electron has to absorb energy, right? When the electron moves from low energy state to higher energy state, this electron has to absorb energy. How much energy it absorbs? Whatever is going to be the energy gap between shell number 1 and shell number infinity, that much of energy gap I need to supply to this electron, then this electron will be going out, then this electron will be reaching towards infinity, right? Okay. Yes? Clear to everyone? Clear to everyone? Let me know fast. Let me know fast. Is it clear? Is it clear to everyone? So basically you are going to make a transition from shell number 1 to shell number infinity. What is the energy possessed by the electron in shell number 1? Energy possessed by the electron in shell number 1 is going to be minus 13.6 Z square, since n value is 1. What is the energy possessed by the electron when it is at infinity? It is 0, right? So what will be the energy gap between this shell and this shell? What will be the energy gap between this shell and this shell? Okay, energy gap, which I'm representing by delta E, which is something which I'm calling as ionization energy as well. Okay, it is going to be equal to E infinite minus E1, which is going to be E infinite is 0 minus E1 is minus 13.6 Z square. So this value, which I call as ionization energy, right, which is equal to the energy gap between shell number 1 and shell number infinity, that's going to be 13.6 Z square electron volts. So this is how we calculate the ionization energy over here, right? Yes? So let me know fast if it is clear. Let me know fast if it is clear. Let me know fast if it is clear to everyone, right? This much amount of energy you need to supply, then only the electron will be moving from shell number 1 to shell number infinity. That means this much of energy you need to provide, then only the electron will go out of the influence of the nucleus, right? Yes? Perfecto? Perfecto? Right? That's great. That's great. People, if you would have noticed one important thing over here, this much amount of energy you need to supply, then only the electron will go out of the atom, right? The electron will go out from the influence of the nucleus, correct? This much amount of energy you need to supply in case of hydrogen-like species, okay? Which is something which I'm calling as ionization energy as well. If I ask you, what is the energy possessed by the electron when it is in shell number 1 of hydrogen-like species? Isn't it going to be minus 13.6 Z square electron volts, right? This is the energy possessed by the electron in the first shell of hydrogen-like species, yes? Okay. This is the amount of energy which the electron carries when the electron is present in the first shell of hydrogen-like species. And how much is the ionization energy of this hydrogen-like species? Ionization energy is 13.6 Z square electron volts. People, is there any similarity between these two formulas? Is there any similarity between these two formulas? It is just the magnitude is same, but the sign is minus, but the sign is opposite, yes? So can I generalize a statement, ionization energy in case of hydrogen-like species is always equal to minus times the energy possessed by the electron in the ground state, which is basically your first shell, right? Okay, so whenever you'll be given with the ionization energy of the hydrogen-like species, from the ionization energy of the hydrogen-like species, you will be calculating the energy possessed by the electron in the first shell. Yes? Okay, right? I'm sure it's clear to everyone. Okay, I'm sure it's clear to everyone. Since hydrogen atom or hydrogen-like atom contains one electron which is present in the first shell, so the transition corresponds from shell number 1 to shell number infinity. This is something which I told you, and this much energy gap, this much amount of energy you need to supply to the electron, then only it will make a transition from shell number 1 to shell number infinity. That means this much amount of energy you need to supply to the electron in case of hydrogen-like species, then only the electron will be going out from the influence of the nucleus. Yes? Okay, right? And so I got a result which I told you, ionization energy for hydrogen or hydrogen-like atom is equal to 13.6 Z square electron volt per atom, and remember 1 electron volt per atom is equal to 96 kilojoules per mole. This is the conversion, you might need it sometimes. Okay? Yes? Perfect. Perfect, perfect, perfect. Guys, if you think I'm going a little fast, you need to change some settings, right? Just watch the video on 0.75x speed. Yes? I hope that works. Abhinash, just watch the session on 0.75x speed. It'll be fine. It'll be fine for you. Okay? Right? Now, there is one more term, one more simple term called as binding energy. How do we define this binding energy? That's the point now, okay? Again, a simple thing. The energy required to remove the electron from the given energy state. The energy required to remove the electron from the given energy state. Let's say this is the nucleus, shell number 1, shell number 2, shell number 3. Let's say the electron is present in shell number 3. Let's say the electron is present in shell number 3. Let's assume you need to take this electron out from shell number 3, right? That means you need to make a transition of this electron from shell number 3 to shell number infinite. Then only I can say I have knocked this electron out. Then only I can say I have knocked this electron out. Or in general, I can say, let's assume the electron is present in the nth shell. The electron is present in the nth orbit. Now, how much energy do I need to supply to this electron such that the electron goes out of the influence of the nucleus? How much energy I need to supply? First of all, I should know what is the energy possessed by the electron in this shell. Energy possessed by the electron in the nth shell is simply minus 13.6 Z square divided by n square electron volts. Okay. And when the same electron will reach at the infinite energy state, its energy will be 0, right? Energy possessed by the electron in the infinite energy state is 0. So if I want to make a transition from this energy state to this energy state, what do I need to do? What do I need to do? I have to supply how much of energy? Whatever will be the energy gap between these two shells, that much amount of energy I need to supply, then only the electron will be moving from this energy state to this energy state, right? Then only, basically, I'll be knocking out this electron. Yes? Okay? Right? So people, binding energy is basically what? It is the amount of energy which is supplied in order to knock out the electron, from the given energy state. Let's say this is the given energy state. I'm knocking the electron out. I'm taking the electron out. That means I'm making the transition of this electron from the given shell to the infinite shell. So how much energy I need to supply? The energy gap between these two shells. And what is the energy gap between these two shells? That's going to be equal to E infinite minus E nth, right? E infinite is 0, E nth is minus 13.6 Z square divided by n square. So this value over here, which I'm calling as binding energy, it will come out to be 13.6 Z square divided by n square electron volts. So this much amount of energy you need to supply, then only you can take any electron out from a given energy state in case of the hydrogen-like species. In case of the hydrogen-like species. I'm sure it's clear to everyone, right? Okay, you can give me some thumbs ups in the chat box if you got it. Now people, you might be thinking one thing. What is the difference between ionization energy and binding energy? Whenever we try to define ionization energy, that means electron has to be taken out from n is equal to 1 to n is equal to infinity. In case of binding energy, you can take electron out from any given state, any given shell, right? From 2, from 3, right? Or I can say something like this. See, this is the binding energy. What was the formula for the ionization energy? It was 13.6 Z square electron volts. This was the formula by means of which we could calculate the ionization energy. So I can clearly say one important thing over here. For N is equal to 1 in hydrogen-like species, for N is equal to 1 in hydrogen-like species, for N is equal to 1 in hydrogen-like species, binding energy is equal to ionization energy. Binding energy is equal to the ionization energy, right? Okay, note this as well, this is important. Yes? Perfect? Perfect, perfect. Let me know fast if it's clear. Yes? Right? Wonderful. Wonderful, guys. Wonderful. This is the binding energy formula which I gave you, right? And for N is equal to 1, binding energy is equal to basically the ionization energy. Now comes one last term, that's what I call as excitation energy. And people, in the next session will be solving the problems which are based on these concepts, okay? Right? The last term, which is something which I call as excitation energy. Okay, how do we define excitation energy? Simple. Whenever the electron has to make a transition from lower energy state to some higher energy state, in case of hydrogen-like species, the amount of energy which is absorbed by the electron to make a transition from lower energy state to higher energy state, that's something which I call as excitation energy. As simple as that, right? Okay. The energy required to excite an electron from lower energy state to higher energy state, that's something which I call as excitation energy. For example, have a look. Let's say this is the nucleus of the hydrogen-like species. Okay, shell number 1, 2, this is 3, this is 4, this is 5, and so on. Let's keep it as, let's call this as N1, let's call this N2, where N1 is the lower energy state in which the electron is present, N2 is the higher energy state, okay? Right? First of all, if the electron is present in lower energy state, how much energy this electron possesses? When the electron is present in N1 energy state, its energy is going to be minus 13.6 Z square divided by N1 square electron volts, correct? This is the energy possessed by the electron when it's present in lower energy state. When the same electron goes to higher energy state, right? How much energy it possesses right here? I'll say En2, energy possessed by the electron in higher energy state N2. It's going to be minus 13.6 Z square divided by N2 square electron volts, correct? In order to make the transition from low energy state to higher energy state, energy is absorbed by the electron. How much energy is absorbed by the electron? Whatever will be the difference between these two energy states, whatever is going to be the energy gap between these two shells, same amount of energy you are going to supply, same amount of energy electron has to absorb, then only the electron will make a transition from this low energy state to higher energy state, right? Okay, so I can say the binding energy, the excitation energy, right? The excitation energy, which is basically equal to the energy gap between N1 and N2 state, right? This is the energy gap between N1 and N2 state. En2, energy possessed by the electron when it is a higher energy state. It is minus 13.6 Z square divided by N2 square minus times En1. En1 is again minus 13.6 Z square divided by N1 square, right? If you solve it a bit, you get something as excitation energy. Whenever you need to make a transition whenever electron has to make a transition from lower energy state to higher energy state, in case of hydrogen-like species, you'll be supposed to supply this much of energy, 13.6 Z square. I'm taking common, so it's going to be 1 divided by N1 square minus 1 divided by N2 square, right? Okay, this much amount of energy you need to supply, then only the electron will be making a transition from low energy state N1 to higher energy state N2. Okay. Yes. So people, with this, your basic concepts are related to what? Are related to energy. I'm sure it's clear, right? These are the things which we have to cover again when I'll be teaching the spectrum, which is going to be in the next session. So people, right here I'm ending the session. But before ending the session, I need to give you one homework question. This is a simple homework question. Basically, I'm going to give you 2 homework questions. And I'm sure you can solve these questions, right? This is the first homework question which you guys are going to do. And this is the second homework question which you guys are going to do, right? These are the 2 homework questions. And based on the concepts which we have discussed in the tonight's session, I'm sure you guys can kill these questions right here. I'm sure it's clear to everyone, okay? So rest everything, I mean the hydrogen spectrum and few more questions based on this, that's going to be done in the next session of the atomic structure. Okay, so at the end, the ones who have not enrolled into the actual Vedantu platform, right? People, you need to enroll yourself in the actual Vedantu platform. Out of these 3 plans, whatever plan you think is suitable for you, you can take that plan, right? You'll be getting trained by us in your physics, chemistry, mathematics, biology, whatever is your subject. If you're preparing for NEET, then physics, chemistry, biology. If you're preparing for JEE, then physics, chemistry, mathematics, right? These are the 2-year classroom programs. Whatever you think is feasible for you, you can take that, right? And no need to pay this much amount in one go. You can pay this much of amount in installments as well. Vedantu has created an option for that. You can pay this much of amount in EMI as well, okay? And at the same time, if you're new to Vedantu, you have no idea how the actual Vedantu platform is all about, what you need to do, Vedantu has kept one more option for you. What is that? You can take these subscriptions for a month, right? These are 1-month plans, okay? If you take these subscriptions for a month, just see if you are getting benefited from it. If you are getting benefit from it, then you can go for the 2-year classroom program, right? Okay, so do give it a try. And how to get enrolled in this, there's a link in the description box of the video. You need to click on the link. You need to use the coupon code as WSPRO if you want me to train you personally in your chemistry, right? Do not forget to use this coupon code as WSPRO. There is one more link in the description box, that's for the Telegram, right? Do click on the link, get added to the Telegram group and stay updated about the classes. And the ones who have not liked the video yet, please and please do like the video, share the video with your friends, and do not forget to subscribe to the channel, and do not forget to hit the bell icon so that you get the notification of every single session which we take live on this NEET Elite channel. So with this, I'll take a leave. It was nice meeting you. I'll see you guys again day after tomorrow. Till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. Bye.